it rewrote the rules of aerial combat. An incomparable combination of aerodynamic agility and lethal firepower, capable of simultaneously firing 6 missiles at 6 separate targets. The jet fighter in a class by itself. Now, the F-14 Tomcat on Modern Marvels. In 2006, an exalted but aging veteran of the skies closed the final chapter in its illustrious history. The last 22 operational F-14 Tomcats, based aboard the USS Roosevelt in the Persian Gulf, flew their final combat sorties over Iraq before being retired from active duty. Although a new generation of state-of-the-art aircraft now flies in its place, the F-14 will always endure as an aerial marvel in a league of its own.
There's nothing like an F-14 when it's doing burner takeoff and things of that nature. It's just still awesome after all these years.
Just the sheer size of it and the fact that the wings had swept always was something that always caught the public's eye when they see the F-14. It's just very recognizable.
There's no other airplane before that or since that has the entire range of capabilities, carrying all kinds of weapons, doing dogfights, doing maritime air superiority, combat air defense.
And has done those things extremely well throughout its history and goes out, I think, as perhaps the most lethal platform on the planet.
The Tomcat's arsenal can include one 20-millimeter cannon, 4 Sidewinder air-to-air missiles, 6 Sparrow air-to-air missiles, 6,000-pound Phoenix missiles, and 4 2,000-pound precision-guided munitions.
They had the ability to cycle between an M61 gun, 20-millimeter cannon. You can go to a Sidewinder air-to-air heat-seeking missile. You can go to a radar Sparrow if you wanted to intermediate range. And you can go with a long-range Phoenix.
Beyond its versatile firepower, the F-14 features a radar antenna with a range longer than that of any fighter jet today.
If you look at some of the other airplanes, fighter airplanes that are out there these days, you'll see that the noses are a little bit smaller, and that means, hey, that their antennas are smaller also.
The F-14's radar can detect targets as low as 50 feet and as high as 80,000 feet. It can track 24 targets and enable pilots to fire their 6 Phoenix missiles at 6 different targets simultaneously. Since these missiles can be fired from almost 100 miles away, the F-14's adversaries at long range have no idea that they are under attack.
It also has defensive electronic countermeasures built into the radar. So it's harder for the enemy to detect and to jam against this radar.
And by the time his radar would have detected you, well, he'd be dead.
It remains today really the benchmark of the multi-mission fighter attack airplane. It's high-speed intercept, Mach 2.4. It's capable of air combat maneuvering. Variable sweep wing gives it a dogfight capability second to none.
The F-14's variable geometry swept wings shift their position based on the jet's airspeed. The wings sweep back as far as 68 degrees at supersonic speeds and can sweep forward to 20 degrees to allow takeoffs and landings on aircraft carriers. Fully extended, the wings enable as much air as possible to pass around them, generating optimum lift. Swept back at higher speeds, the wings minimize the F-14's drag. Another signature feature of the Tomcat provides its prodigious thrust. Twin turbojet engines.
There are 2 series of engines that have been used in the F-14. The oldest is the Pratt & Whitney TF-30 engine. It had about 17,000 pounds of thrust available. The follow-on for that engine was the GE 110 that all the Bs and the Ds are flying today. It has about 10,000 pounds more thrust per engine, so a total complement of about 56,000 pounds of thrust.
The afterburner capability of this GE F110 engine allows this airplane to accelerate to speeds in excess of Mach 2.3, which is approximately 1,500 miles per hour if you're looking at your speedometer.
At such lightning speeds, controlling the rush of air entering the jet engine's intakes is imperative.
This is one of the intakes for the F-14B that we're looking at here. Since this is a supersonic fighter, we have to kind of slow down the air before it hits the motor. If supersonic air does hit the motor, it'll stall it. So when they developed the F-14, they developed an air inlet control system, which allows these ramps, there's actually 3 ramps, number 1, number 2, and number 3 ramp. These program down as a function of your Mach number. And the faster you go, as you approach supersonic speed, Mach 1, all these ramps will be deflected down, decreasing the air that goes in here. So it controls the amount of flow that goes into the motor.
The F-14's superb aerodynamics are matched only by its prowess as a combat fighter. To hunt ground targets, it relies on the lantern, short for low-altitude navigation and targeting infrared for night. Its infrared imaging system can identify targets from altitudes of 40,000 feet. Then the pod's laser can fire a beam to the target to precisely guide the F-14's 2,000-pound smart bombs. A separate piece of hardware helps the F-14's pilots home in on air-to-air targets.
This is the TCS camera system, television camera set. And the unique thing about this with the F-14 is it allows me to slew this to where the radar is pointing, and I could actually get a contrast log on an unidentified aircraft out there. Take a look and put it on my display, and it allows me to identify an airplane before I could see it within the visual range.
In other words, this video system acts as the pilot's long-range eyes, helping him distinguish between friend and foe in the sky. The Tomcat can come equipped with yet another targeting device called TARPS. Short for Tactical Airborne Reconnaissance Pod System, it provides clear digital still images of targets up to 600 miles away.
Go in and fly for more than 1,000 miles, go in deep into enemy territory, get pictures, photographs.
Such impressive features embodied in such a nimble and deadly aircraft have combined to grant the Tomcat a mystique all its own. The origins of the F-14 date back to the early 1960s, when America's Cold War with the Soviet Union was heating up. The Russians were developing a large family of surface-to-surface cruise missiles that flew extremely low. At such low altitudes, there were more signals that could interfere with the radar on U.S. ships, which might be unable to detect these missiles until they were too close. The Soviets also possessed deadly air-to-surface bombs. U.S. fighter planes didn't have the ability to intercept them.
The Russian attack aircraft that could come in from, hundreds of miles away and do a pretty devastating job at a carrier group if they got too close.
The Pentagon realized it needed an aircraft that could take on the Soviets.
We needed air superiority, which required an air combat maneuverable fighter aircraft, capable of being nimble and agile and dogfighting.
The plane also needed to carry a powerful radar system to help it quickly intercept an enemy missile.
And that was the ability to protect the carrier fleet and to be able to go out hundreds of miles and detect anybody that's incoming from a long range.
In November 1962, the Pentagon awarded the Grumman Corporation a contract to build an interceptor version of a fighter already in development, General Dynamics F-111. Grumman's F-111 for the Navy began flying on May 18, 1965. But it had several problems. It was a whopping 85,000-pound fighter, too difficult to land on an aircraft carrier, and its swing wings had to be operated manually by the pilot.
What the Navy really wanted was a fighter aircraft, and the fighter aircraft that the F-111 represented wasn't a particularly good fighter. It was too big, it carried too much fuel.
By 1966, the problematic F-111 had become a time-consuming headache for the Navy, prompting its leaders to create a new jet fighter with a demanding set of requirements. Mach 2 speed, great maneuverability, a powerful radar, and the ability to carry a variety of weapons. Furthermore, the new plane had to be light enough to take off from and land on an aircraft carrier. During the summer of 1968, the Navy solicited engineering proposals for the new fighter from 5 leading aerospace contractors. In January 1969, Grumman again was declared the winner. Its $5 billion military contract was the largest in history. But the contract was demanding. Grumman was bound to deliver 700 airplanes over 8 years. Even more daunting, it would need to have a plane ready for a test flight in 17 months, half the usual time for a program of this type.
From contract signature to the delivery of the airplane, we had a requirement of 51 months.
Work on the plane began in August 1969. One of Grumman's first decisions was to include a feature originally designed for the Air Force's YF-12 Blackbird and adopted by the F-111B, the AWG-9 Doppler radar system. This was a significant improvement over pulse radar from World War II, which was still used on aircraft carriers in the 1960s. Pulse radar measures distances from targets. It works effectively in the open sea, but closer to land, stationary features like mountains clutter the radar operator's display. Doppler radar only measures moving targets without regard to background. It could easily detect Soviet cruise missiles. While the F-111 had only 2 forms of pulse radar and 2 forms of Doppler, the new plane would have 6 radar modes, 4 in Doppler and 2 in pulse. This doubled the number of targets the jet could track from 12 to 24. And it could counter the cruise missiles from greater distances. With a proper air-to-air weapon, the jet could theoretically down the Soviet missiles.
The AWG-9 was an excellent transfer to the F-14. We needed it for the excellent range it has and for its excellent capability.
Developing a sophisticated radar system for the new jet fighter was one thing. Designing the new state-of-the-art fighter itself was another. To answer the challenge, Grumman engineers would have to reinvent the basic components of the military aircraft. In 1969, after landing the $5 billion contract for the F-14, the Grumman Corporation set its sights on the new fighter plane's design. Engineers faced the sobering challenge of designing a jet plane that had to travel at Mach 2 speeds and maneuver spryly in battle while carrying tons of weapons. Grumman's first priority was the swing wing. The concept is simple. A swing wing enables a plane to fly faster by reducing the wing's frontal area and the plane's overall drag. In May 1952, Grumman had developed the first Navy swing wing plane to fly, the XF-10. But it was plagued by a variety of engine, stability, and control problems. In 1953, the XF-10 program was scrapped, but the swing wing concept had shown great promise.
We learned an awful lot in the process of doing it. And after that, we were teamed with General Dynamics in the production of the F-111 aircraft. There was another case where Grumman got very valuable experience in dealing with variable sweep wings. We pretty well had a grip on what not to do when the F-14 program came along.
But not at first. Designer Bob Kress and some of his colleagues disagreed about the airspeed at which the F-14's wings should be swept back. Kress's fellow designers felt that speed should be Mach 1.2, or 900 miles per hour.
When the fellows came in and dumped that number on me, I was quite shocked. And I started to ask, what would anybody be doing at Mach 1.2? With the wings unswept, the airplane would be screaming at them.
Before the F-14, pilots flying swing-wing aircraft were responsible for sweeping the wings back. Kress felt a system was needed that would relieve pilots of concerns about the swing wing's optimum position. His team devised an air data computer called the Mach Sweep Programmer. It would automatically sweep the wings without any input from the pilot.
That's probably the most unique characteristic of the airplane in the sense that it provided the first truly computer-controlled operational variable swept-wing aircraft. The pilot could override the computer if there was a computer failure.
Kress's team subjected the wings to countless wind tunnel trials.
What we did as the Mach number increased beyond Mach 0.7, we gradually started to sweep the wings back until they were at full sweep at about Mach 0.95. There was tremendous compatibility between limitation of bending moments and making the airplane a superb fighter in terms of drag and buffet and turning performance.
Weight considerations were a key factor in choosing what material would be used to construct the swing wings. Since the F-14 would carry tons of weapons, Grumman chose titanium, which is both lighter and stronger than steel. Welders fused several pieces of titanium together to form a key part of the F-14's airframe, the wing box.
The wing box structure is the structure that effectively went from one side of the aircraft on its wing pivot to the other side of the aircraft on that side's wing pivot.
The titanium box beam was a marvelous piece of engineering. It weighs 2,500 pounds, and it's all welded together. It holds the whole airplane together.
The completed wing box and airframe showcased their structural integrity during more than 500 test drops. The F-14 would be made up of 35% titanium. While its wing box was composed entirely of titanium, the rest of the aircraft would consist of approximately 40% aluminum alloy, less than 1% boron, and about 18% steel. The F-14's high percentage of titanium helped make it 40,000 pounds lighter than the F-111. Its trim physique would enable it to increase its thrust-to-weight ratio, a crucial measure of aerodynamic performance. The ratio is calculated by dividing an aircraft's thrust, measured in pounds, by the aircraft's weight in pounds. The greater the ratio, the better the performance. In order to achieve the ideal thrust-to-weight ratio, Grumman engineers began an exhaustive series of tests, with most of the emphasis on the swing wing. They subjected models in more than 2,000 configurations to over 9 tunnel testing. By January 1968, they'd found their ideal model. Number 303E, a swing wing craft powered by twin jet engines, each producing 20,000 pounds of thrust.
The twin engines were significantly separated from one another. And early on, we didn't really realize how valuable that separation would become as a place where we could nest missiles one behind the other. Missiles as big as the Phoenix missile and as big as 2,000-pound bombs.
The F-111 had an internal bomb bay and permanent fittings for carrying the 6 Phoenix missiles. The Tomcat carried its weapons externally.
It's what we call the pallet concept. And if you look at the bottom of the F-14 airplane, you'll see the 2 Phoenix missiles for 2 2,000-pound bombs. They're located on rails, and the rails are contoured such that the fins of the missiles and part of the missile is covered by the rails, which cuts the aerodynamic drag of the weapons.
Weapons crews could change the pallets quickly depending on the mission. Another innovation by Grumman engineers was the F-14's twin vertical tail design. This configuration had never been used before in any jet fighter. 2 shorter tails, as opposed to a single taller tail, would make it easier for pilots to maneuver the plane on carrier hangar decks with height limits. But most importantly, the 2 tails would create greater directional stability.
When you have 2 tails, you have twice as much surface that can be applied to the aerodynamic forces. You can get twice as much correction factors. You want something that straightens the airplane out. If you lose an engine, it tends to slide laterally and rotate. You want it to stop rotating.
Another revolutionary design concept came from Bob Kress, the crew of two. The pilot and the RIO, or radar intercept officer, would be seated in tandem. This configuration would reduce the plane's drag because it would make for a thinner cockpit. The target date for the test flight of the first of 12 prototypes was January 1971. Grumman planned to get its first innovative bird in the air a month ahead of schedule. Confidence was running high, but looming ahead were unexpected dangers and sudden death. The first of what would be thousands of test flights for the new F-14 was planned for December 21st, 1970, a month ahead of schedule. The location? Grumman's Test Flight Center in Calverton, New York. Robert Smythe and Bill Miller were the test crew. As darkness fell, the prototype made 2 wide circles around the airfield, completing a simple but successful 10-minute flight. Test flight number 2 came 9 days later, on December 30th. This time, the plane was to make its first efforts to go supersonic and sweep the wings. Smythe and Miller would again be in the cockpit. Flight test engineer Dennis Romano followed in a chase plane.
There was a lot of hoopla, and there were a lot of people there. The F-14 got airborne and flew out off the south shore of Long Island. There was a good stiff breeze blowing, probably about 25 knots.
The flight began smoothly, but miles away from the base, at 10,000 feet, the F-14 started leaking hydraulic fluid. The leak was caused by a resonance, the rhythmic shaking produced by pulsations from the hydraulic pumps. This led to a break in the hydraulic lines. The pilots were forced to bring the plane back.
We lost the hydraulic power for the controls, so we tried to get it to the field, and he almost got back, and all of a sudden the airplane started to fishtail. And they just speared in this plume of smoke because they were going down with the airplane. And I felt I had lost 2 friends.
I saw the backseat guy, Bob Smythe, and the front seat guy, Bill Miller, come out. They ejected. I saw Bob Smythe's parachute descending into the exploding fireball. Heat from the rising fireball lifted him up, and the wind blew him after the wreckage. And the bottom of his flight suit was singed from the heat. But they both escaped. The aircraft, unfortunately, was completely lost.
And all it took was to go and change some of the clamping on the hydraulic, and the problem went away.
5 months later, the same test pilots, Miller and Smythe, successfully reached supersonic speed and deployed the swing wings for the first time. In the months to come, Grumman continued its trials, conducting 600 separate tests with each flight. Sensors transmitted information to engineers manning computers. They would examine the data, then clear pilots for the next test flight.
Let's say out on a wing panel, you had 50 stress points on the wing that you wanted to measure. Each wing, you put 50 instrumentation points. And these are little sensors, and each one of those is a parameter. 600 of those are being recorded constantly. Some of them are electrical, some of them are stress, structure, engine, fuel system. And what you happen to be testing primarily that day is where the focus and the emphasis is. We could go out and continue to do our testing until the engineer on his flight test console would see some sort of a danger point and decide at least we would stop that portion of the test, but then go on to some others.
The structural test program was the most demanding phase for both plane and pilot. The F-14 flew every maneuver imaginable at low speeds, high speeds, and at all altitudes.
Sometimes, depending upon the flight configuration and the loading of the airplane, we would roll the airplane as high as 270 degrees per second. And for an airplane that weighed 40,000 pounds, that was pretty good. A lot of inertia. We did that at twice the speed of sound. And we also did it at 900 miles an hour at 5,000 feet.
Up to 135 structural test points were assessed in a 4-hour flight.
And I will tell you that even for a young man at the end of a 4.5-hour structural flight, you were pretty worn out.
The rigorous test flights finally exacted a terrible price. In June 1971, Bill Miller, who piloted the first flights, mysteriously lost control of his plane and died in a crash. But the testing continued. The most vexing problem proved to be the F-14's engine. The same basic model that Grumman had been contractually bound to use for the F-111. Grumman had installed Pratt & Whitney's TF-30 engine on most of its test and all of its production F-14s. The engine had difficulty coping with both extreme aerodynamic maneuvering and high load stresses.
Every time you fly, you're stretching the envelope. You're not just flying straight and level like a regular jet passenger airplane. You're flying very fast. You're stressing it aerodynamically, inertially, every which way.
Sometimes fan blades broke off and flew through the rest of the engine, destroying it entirely. Engineers solved the problem by developing engine improvements, including stronger titanium alloy fan blades. They also added steel containment bands to the fan cases to prevent damage to the aircraft during possible engine failure. Additional improvements like this one enabled the F-14 to live up to its potential. Over the next 18 months, only 2 more planes were lost. But the most crucial and intricate test was yet to come, one that required the plane to fire 6 Phoenix missiles simultaneously at 6 separate targets.
You have to have 6 separate drones flying in 6 different places, and you have to have an F-14 with 6 Phoenix missiles, and you have to have all the range and all the coordination capability. A big deal.
Nobody has ever attempted to fire at 6 widely separated targets simultaneously.
The pioneering test would take place at the Naval Missile Test Center at Point Mugu, California, in November 1972. The F-14 would fire missiles at targets flying at altitudes ranging from sea level to 100,000 feet.
Fox 1, 1's away, 2's in the air, 6 in the air.
Only one of the 6 missiles failed to hit its target.
Hit 5 directly, smashed right into them. It's incredible. And the one that missed, I don't recall exactly if it was within lethal range, but it wasn't far off.
The Navy was sold. 3 months after the 6-on-6 test, it took delivery of its first F-14s. The Tomcat program hit stride. Over the next 3 decades, thanks to ongoing improvements, the F-14 would repeatedly prove its worth in combat. But in 1979, America's attempt to help an ally would spell near disaster for the Tomcat and the United States. Shortly after its delivery to the Navy in 1973, the F-14 became one of the most respected fighters in the sky. But the same year, Soviet aggression prompted an unusual decision involving the Tomcat that would put America in a very vulnerable position. Iran, then America's ally, was concerned about the Soviet MiGs that were entering its airspace at 50,000 feet. MiGs were able to fly at speeds exceeding Mach 2. The Shah of Iran asked President Richard Nixon for help intercepting the supersonic intruders. Nixon told the Shah he could order either the F-14 Tomcat from the U.S. Navy or the F-15 Eagle from the Air Force.
The only airplane that was really capable of taking down the MiG-25 was the F-14 with the Phoenix missile on the Phoenix missile system. The F-15 was appealing to the Shah because it was an Air Force aircraft, and there were a substantial Air Force presence in Iran.
The Shah asked to make his decision based on a fly-off or air show featuring the 2 planes. Nixon agreed. The fly-off occurred at Andrews Air Force Base in Maryland. The F-15 flew first. Then the Tomcat took to the air. Dennis Romano was aboard as the radar intercept officer.
90-degree turn to the right, a 270-degree turn back to the runway heading, flew down the runway at 500 feet in a 90-degree bank. and swept the wings forward from 68 degrees to 20 degrees while we were doing that maneuver. We touched the airplane down and then pulled the airplane up into a vertical climb, left the gear and flaps down, rolled the airplane directly over the end of the runway, which was very impressive.
The Shah chose the Tomcat, in part because the F-15 had been experiencing ongoing engine problems. In January 1976, the Navy delivered the last of 79 F-14s to Iran. With the exception of a few classified avionics features, the Iranian Tomcat was identical to the U.S. Navy's. Grumman technicians and pilots provided training and technical support. Then, in early 1979, America's relations with Iran suddenly disintegrated. Increasing unrest in Iran led to the overthrow of the Shah. Now in power was the radical Islamic government of the Ayatollah Khomeini. 79 of America's elite fighter jets were in the hands of an enemy. Then came a new twist to the story. By August, the Iranians had discovered that every Tomcat in their arsenal was incapable of firing its missiles. What happened remains unclear to this day, but some suspect that Grumman technicians sabotaged the F-14s before they evacuated.
The rumor that I heard was that they took some of the electronics as they were leaving. I do not know whether that's a fact or not.
What is known is this: an arms embargo imposed against Iran by the U.S. crippled Iran's efforts to supply parts for the F-14s and to provide necessary maintenance.
There are very detailed inspections and parts that have to be replaced on a regular basis. And if you don't maintain it, in a couple of months, it'll just go into complete disrepair. And I think that's what really happened. The real knowledge base was the group of technicians that had gone to support the F-14. Once they lost the parts and once they lost the expertise, just a matter of time.
As far as we know, the airplanes are essentially sitting in desert storage with very little usage and no spare parts.
In 1981, 2 years after the intrigue in Iran, the Tomcat exhibited its prowess. It began when the USS Nimitz entered the Gulf of Sidra in the southern Mediterranean, which Libya had claimed as its own territorial waters. The Nimitz's purpose was to demonstrate right of navigation in defiance of Libya's so-called line of death. The Nimitz's Tomcats came under fire by Soviet Su-22s, flown by Libyan pilots. The Tomcat shot down both Soviet jets. 8 years later, Libyan pilots again confronted the F-14.
Goes up 53 miles now.
This time, they were flying the swift and mighty Soviet MiG fighters.
Second engagement, we actually tried 4 or 5 different maneuvers to avoid the airplanes that were oncoming. And each time we made a turn, they turned into us, which meant that it was a confrontation.
You stink back into me for the 4th time and box one again. Good hit on one. Good hit. Got the other one. Good kill. Hey, good kill.
Once again, 2 Tomcat crews shot down 2 Libyan fighters with relative ease.
That was actually almost Sidewinder 101. They've never really been challenged, and they'd like to be.
Despite the F-14's superiority, experts felt that by the end of the 1980s, the plane would eventually be phased out and replaced by newer fighter jets. But improvements made over that decade and the 1990s would extend the Tomcat's effectiveness. One of the most important upgrades involved the F-14's engine. The primary concern with the F-14 during its first decade of service was the possibility of engine compressor stalls. The earliest generation of engines was ideal for supersonic speeds, but not for extreme combat maneuvers.
The airplane was a fighter, and as a fighter, there are a tremendous number of rapid throttle excursions.
You had to watch carefully to make sure you didn't get it too high angle of an attack, get too slow or whatever, get outside the allowable envelope.
The stalls occurred at high altitudes and low speeds, triggered by irregular airflow. Left uncorrected, the aircraft could begin to spin uncontrollably. This scenario doomed some 19 F-14s in 1984. After the Navy installed the newer General Electric engines, pilots could fly through extreme angles of attack and maneuver without worrying about compressor stalls.
The GE F-110 engine really provided the thrust and the performance to the airplane that it had been originally designed for. The GE engine increased the afterburning thrust, total thrust in the airplane from about 21,000 to over 28,000. This is about a 40% increase in thrust. It also provided a computer fuel control, which gave us stall-free operation throughout the envelope.
In the early 90s, a new digital radar system gave the F-14 another performance boost. With the APG radar, the Tomcat could now track targets at nearly 200 miles from almost any altitude. And in 1995, the Lantern, developed by the Air Force, gave the F-14 laser-guided weapon capabilities. Tomcats used the Lantern for the first time in 1996, when they dropped precision-guided munitions over targets in Bosnia. This earned them the nickname Bombcats. The F-14 had shed its 70s-era technology, and it became a smarter, more effective aircraft. The original plane had only 3 computer processors. The latest versions have 33.
So you always had your main central computer, but now you have distributed processors all over the airplane doing all kinds of calculations.
But despite the Tomcat's wide variety of upgrades, military leaders began to determine that its days as America's top fighter jet were numbered. The time had come to make room for a new generation of combat aircraft. The proud old plane had a date with the junkman. For 3 decades, the F-14 staked its claim as America's premier air defense fighter. After helping to win the Cold War, it reasserted its strategic stature in the skies above Bosnia, Kosovo, Afghanistan, and Iraq. But by the early 1990s, the Tomcat had become too difficult and expensive to maintain. Part of the problem was the complexity of its design, including its variable geometry wings. Another factor was the harsh salt air environment it inhabited on aircraft carriers. For every hour the F-14 was airborne, maintenance crews had to expend some 40 to 60 man-hours to keep it operational.
It's certainly still very capable, better than most airplanes in the world's inventory. Has some awesome firepower to it, lethality to it. But it is an old airplane. The sailors that work on it work very, very hard to keep it up and keep it flying.
We really started in earnest phasing out the F-14s in about the early 90s time frame. The aircraft was approaching 20 years old. Many of the original aircraft were starting to reach the end of their service lives. So we started transitioning squadrons from 2 squadrons in each battle group down to 1 squadron in each battle group. At the same time, the F-18 Hornet was coming online, so it was starting to take some of the missions that the F-14 could fly.
The Navy finally decided to withdraw all remaining Tomcats by 2006. Each retired jet first comes to Oceana Naval Air Station in Virginia. Here, experts determine its ultimate fate.
Some of those aircraft are destined to go to museums throughout the United States or military bases throughout the United States, be placed on public display. Some of the aircraft will go to what we call AMARG, which is at Davis-Monthan Air Force Base in Tucson, Arizona. That is a storage facility that military aircraft go out there in case we ever decided to bring a Tomcat back into service for some reason. We'll keep a certain number of Tomcats out there.
The remaining F-14s stay here at Oceana, where teams of mechanics strip their parts in preparation for a date with the shredder. It's all part of the Navy's Stricken Aircraft Reclamation and Disposal Program, or SARDIP. William Bell of Titan Systems spearheads the project.
After 30 years of maintaining the F-14, being involved in the management and control of the aircraft, trying to extend the life as long as we possibly could, and seeing it in service for 30-plus years, it's a very bittersweet scenario for me to be the guy that also is in charge of making them go away.
On this day, Former F-14 maintenance crewmen Larry Brown, Matt Cullen, and Tyrone Pickett are stripping a Tomcat that once soared proudly over Iraq in Operation Iraqi Freedom. It's now known simply as number 161428.
Each aircraft is assigned a bureau number, and for us to make it easy for us, we just assign write the bureau number on the part and pretty much track it that way.
It will take them about 2 to 3 weeks to carefully remove and catalog close to 500 separate parts.
I spent all those years maintaining them, and now I'm actually tearing them apart, and it's sort of hard to tell you the truth. I guess the first one was the worst, but, you know, just like anything else, you get used to it. We usually take out the ejection seats first because of the explosives in them. Then the avionics, get all the confidential gear and things of that nature, all the boxes out.
In this compartment here, we'd have many of the radar-type boxes, weapons-type boxes that would come out. All of these type items, and these are the type components that we would remove from the aircraft, and those would go back into the naval supply system to be reused on either other F-14s, and some of these components may even fit other aircraft, that they would reuse those on those.
Each part stripped from the plane must be meticulously accounted for. This will help ensure that none of the parts falls into the wrong hands, like those of the Iranians, who still possess their fleet of inoperative F-14s from the 70s.
With the Iranian situation and the Tomcats, and the fact that we know that they would love to have a lot of our parts as we get rid of the F-14s to try to get theirs back in service, control and accountability of our components during the startup process is critical.
Reduced to wingless carcasses, the Tomcats slated for destruction are unceremoniously towed to a site aptly known as the Boneyard.
When it comes time to cut one up here, it's almost like losing a member of my family. It's been part of my life forever.
The cut-up remains of the aluminum airframes are later shredded and recycled. You'll never know if the body of your new car or your can of soda once hurtled through the sky at Mach 2, defending America's interests. Whether an F-14 is scrapped or shipped to a museum, you can be sure that there's a crew member who had a tough time saying goodbye.
As you deliver an airplane to a museum like that, you let the fuel burn itself out, so you don't shut the engines off. You wait until they die, and it's really the final death of the airplane, and it kicks hard, and it chugs, and it tries to keep breathing and fighting, and boy, very, very emotional day.
A new breed of combat fighter now rules the skies. But the F-14 will endure as the pioneering wonder that changed the face of aerial warfare. A plane not measured simply by its superior abilities, but also by its indelible mystique.